Okay, so let us do some problems to practice more on static equilibrium in case you will have it for the midterm. Okay, so as usual, whenever you have a problem of equilibrium, in case it's a point equilibrium problem, you will just apply sum of forces equals 0. And in case it's a rigid body, just you have to apply sum of forces and sum of moments equals 0. Do you see the screen or not yet?
Not yet. Now we do.
Okay. So let us start with some of the problems. We have in the following figure, the C bracket is supported at A, B, and C by rollers. We want to determine the developed reactions at the supports. So first, as you can see, this is a 2D equilibrium problem because we want to find what are the reactions at A, B, and C required to keep our structure in equilibrium. So to start with, we should draw the free body diagram. The free body diagram will always represent all forces acting on the object, including the external forces that you apply and the reactions at the supports. So here the only external force is F. And since we have 3 rollers, as you can see, whenever you have a circular symbol, this is a roller. And keep in mind that the roller can always develop a reaction that is perpendicular to the contact line. Okay? And it is always directed from the roller towards the object. So A here will develop a reaction perpendicular to contact downward. So this is the reaction at A. For points B and C, it's a little bit more challenging because the contact line is not horizontal or vertical. So you can see here that part BC belongs to a circle. And you know that for a circular contact, the normal is perpendicular to the tangent line, so it is along the radius. So here, since they gave us the radius direction at B and at C, so I can say that the reaction at B will be perpendicular to contact, so it's perpendicular to the tangent line. This is the reaction at B. Similarly, at C, I can do the same procedure. So this is the tangent line, and this is RC. So in total, I have in this problem 3 unknowns. Okay, my unknowns are reaction at A, reaction at B, and reaction at C. All other parameters are given. I have the magnitude of the force F. I have the angles θ1, θ2 that will help me in case I need, for example, to project my forces, RB and RC. And I have the dimensions A and B for distances. Okay, so now I have to write 3 equations that will allow me to solve for my unknowns. As I told you before, you can have a variety of equations, or you can write sum of x equals to 0, sum of y equals to 0, and the third relation will be a moment about any point of that is convenient, that will simplify the equation, equal to 0. And also, you can replace the force equations by moment equations if you want. But in general, force equations are easier to write than moment equations. This is why we'll use force projections, and we select one point in a way that sum of moment will give us a simple equation. For example, if we take this figure, okay, we already determined what are our external force. Which point do you think will be the easiest one to do sum of moments about? If you look well at your figure, RB and RC both pass by 1 point, okay, which is the center of this circle. So this is point O. And because of this, RB and RC will not have a moment about O. Okay, so the best point to select here and do sum of moment about is O. Because when I do sum of moment about O, RB will not have a moment, RC will not have a moment, and I only have the moments of F and RA. And since F is known, so the only unknown will be RA, so I can get RA unknown from doing sum of moments about O. So I can start by the first equation, sum of moments about O equals to 0. Now, as I told you before, always consider a certain positive direction. So you try close to your equation. Guys, please, if you are not asking questions, when you don't ask questions, please mute your microphone. Shabab, please, when you don't ask questions, mute your microphone. So this is, let us say, the positive direction is the counterclockwise direction. If you look at your figure, you have F is tending to rotate about O clockwise. Because if you do this with this is O. If you just do this with your hand, how is F rotating about O? Is in the clockwise direction. So, and since you selected the counterclockwise as positive, so it's minus F times, you know that you should multiply when you calculate the moment, you should multiply by the perpendicular distance from O to the line of action of your force. Or also you can say the line of action of my force is vertical. So the distance will be the distance between these two lines. And this distance, as you can see in the figure, is equal to B. Okay, so I should multiply F by B to get its moment about O. And this moment is negative because it's rotating counterclockwise. On the other hand, at A, RA is downward, but now it's from the other side of O. So if you look at the moment of RA is tending to rotate about O in the counterclockwise direction. And what is the distance between the parallel line to F passing by O and force F and force RA passing by A? The distance is A. So then I can say that to calculate the moment of RA, it's a positive moment, and I should multiply the reaction at A by the distance A. So it's plus RA times A. This is my first equation. In my first equation, the only unknown is RA. So I can say that R of A is equal to F times B over A. Okay, and I am done with my first unknown. Now, once I determined RA, the only remaining unknowns are RB and RC. So I just have to write two equations with two unknowns to get the values of RB and RC. And of course, the easiest equations will be the two projections on X and Y. Because if you decide to take any other point and do moments about, it will be challenging. If you want to do sum of moments about B, you should decompose RC into two components and get the moment of each of these components about B. Or you should get the distance, which is not very easy to find. So if you have here, this is the line of action of RC. If you want to find the distance from B to RC, you need to find, here it's not very difficult. You can find it geometrically. So you can say this is the perpendicular, this is distance D. And since I know the value of this radius, so this distance is B, and I know the total angle θ1 plus θ2, I can say that D is B times sine θ1 plus θ2. So I can, because it's easy geometrically to get the distance here, it's fine. You can do sum of moments about B if you want. But also for other forces, the distance is not very, very straightforward. You should do calculation to get other distances also. Because if you want to do sum of moments about B of F, you need to determine what is this distance. Okay, so you should decompose it into two parts. So it's challenging. It's not a straightforward point. So you can see the selection of the point is very critical. If you can select a very simple point like O, and sum of moment will be quite simple. However, for other points, you might need to find distances, use geometry. So always try to take a look and select the point that is the easiest to find sum of moments about. And then once you have RA, to get your two additional unknowns, just use sum of x equals 0, because always force projections is much easier than in general than moment equation, unless the moment equation is very simple, like the one about O. So sum of x equals 0 and sum of y equals 0. Let us decompose our forces. Already RA and F are very simple. They are just along y direction. So you just still have to decompose RB and RC. And this is relatively simple because, as you can see in the figure, they gave you the angle between the vertical and these two forces. So when you want to project RB, okay, RB has a positive projection on Y. Let us choose another color for the projections. It has a positive projection on Y. And as you can see from the figure, this angle is equal to this one. This is theta 1. So the projection of RB on Y is RB cosine theta 1, while the projection of RB on X will be plus RB sine theta 1. Okay? You will do the same for the reaction at C. Now, just for C, the difference is that you have a negative X projection, positive Y. So you have positive Y, which is R C cosine theta 2, and negative X, which is minus RC sine theta 2. So when you write your equations, for sum of X, no component of RA and F along X. So in sum of X, you just have plus RB cosine theta 1 and minus RB sine theta 1 equals to 0. And for sum of Y equals to 0, you have to consider also the component of RA and F. Both are in the negative downward direction. So you have minus RA, which is already calculated, minus F, plus RB cosine theta 1, and plus RB cosine theta 2 equals to 0. Sorry, here it's sine. In X, it's sine theta 1, okay? In Y, it's cosine. So plus R C. So plus RC sine, cosine, sorry, theta 2, okay? And now you will obtain two equations with two unknowns. Let us see them in a clearer way. Here they are represented in a clearer way. Let us read the equations. So as you can see, this is the first relation of sum of moments about O. You can see the free body diagram here, okay? You have the moment of NA and F about this point. Then you move to projecting on X direction. Along X, as we said, you have the positive projection of RB and the negative projection of RC. So it's plus RB or NB sine theta 1 minus RC sine theta 2. The same now for sum of forces along Y. These are the projections of RB, RC along Y. We multiply by cosine theta 1, cosine theta 2. And we don't forget to subtract along Y and A and F. So now, first equation will give you an A or reaction at A. And the two other equations will give you a system of two equations with two unknowns. The two unknowns are RB and RC. You can get them. Okay? Any question on this problem? Okay. Another problem. We have the following car is being towed at a constant velocity up the incline using the cable at C. The car has a mass M and a center of mass at G, and the tires are free to roll. Determine the reactions on both wheels at A and B and the tension in the cable at C. So in this example, you have several forces acting on your car, and they told you that it is moving at constant velocity. So this is what we call dynamic equilibrium. So we have motion. This is why we say it's dynamic, but we don't have acceleration. So this is why we say we have equilibrium, because sum of forces will be equal to 0. Okay. So in order to solve for our unknowns, we'll use the concept that since we have a dynamic equilibrium, A is 0. So by applying a Newton law, sum of forces on our car is equal to 0. So now the first step in any problem like this is to draw the free body diagram showing all forces acting on your car. So to start with, you have a cable that is pushing, trying to pull the car upward. You have the contact at A and B. You have a normal reaction at A. You have a normal reaction at B. And you have the weight passing by G. Okay. So now, if we want to start from somewhere, okay, we should determine first what are our unknowns. In this problem, we don't know the tension in the cable, and we don't know the reaction at A and the reaction at B. So we have 3 unknowns, and as you know, for a rigid body, I can write 3 equations for 2D equilibrium. I can write sum of forces equals 0, and also I can select any point of interest and say that sum of moments is 0. Okay. So first, let me think which are the easiest equation to write. I can try to select a point where it's simple to do sum of moments about. Sometimes we don't have any point that is very simple to use, so we select any of the possible points. Okay. Now, for example, if we select, let's say, A or B as a point, then we cancel out the moment of NA. Okay. If we select C as a point, we cancel out the moment of F. It's a good idea to take C, because in this way you will not have to decompose the force F into 2 components and get the moment of each component about the point, but you will still have to decompose then the weight. So always here, whatever you select, you should do some decomposition, but it's fine. You can select, let's say, or C, or A, or B, or G if you want as point. So for example, let us choose C. Example, if we want to write sum of moments about C, okay, equals to 0. First, as we said, so we write sum of moments about C is equal to 0. And we say that first, F will not have any moments about C, so we are done with it. Now, concerning the weight here is the most challenging part for the moment about C, because as you can see, for the weight, in order to, you have 2 methods to find the moment of the weight about C. The first method is to say, can I find the distance, the projected distance from the force to point C? So if I do the perpendicular from C to the line of action of the weight, is it easy to calculate it? Let me check. So what can I say first? First, I have that this distance, okay, is in a way to be perpendicular to the weight. So this distance is horizontal. Okay, let me put it clear. It should be a horizontal distance. Okay. Now, for this, to get this horizontal distance, I need some geometrical information in my problem. So do I know, for example, an angle here or anything that could be helpful for me? What I know is that, yes, because look, I know that the incline this line here. Okay, I know that this angle is known. This angle is theta 1. Theta 1 is 20 degrees. Okay, so since I know that this is 20 degrees, and I know if you want the distance between C and if I consider this distance here in my figure, look, if I take this distance, this distance is known, it's D plus C, okay? So this is D plus C, okay? And I have that the angle between the incline and the horizontal is known. This angle here is equal to theta 1. So if I want to find the perpendicular, if this is the perpendicular distance, okay, between, so if I say I want to get what is the perpendicular distance between the weight and point C, I can say that this perpendicular distance is doing with D plus C an angle of theta 1. So I can determine what is the horizontal distance from the weight to point C. I can say that this distance of interest, if I want to get the moment, is equal, in this right triangle, to find this distance, I just have to multiply, if you want, D plus C by sine of theta 1. Okay, so I can say that it's equal to D plus C times sine theta 1. And then once I find this distance, I can say that the moment of weight about C is equal to this distance times W. And the moment is in the clockwise direction about C. Now I still have the moment of the reaction at A and the moment of the reaction at B about C. So this is RA, this is RB.
دكتور
نعم.
مش كوساين ثيتا؟
بلا cosine theta, yes. Cosine theta 1, exactly. Cosine theta 1, okay? And now, to get the moment of RA and RB about C, I determine the distances, okay? So I have first, this distance is D. So for RA, the distance is D. And since my force is upward, so it will do a moment about C into the counterclockwise direction. So to get the moment of RA, I multiply RA times D. And finally, to get the moment of RB about C, okay, I multiply by the whole distance here, which is D plus C plus B. Okay, so in total, what do I get? I get two positive moments for RA and RB and a negative moment for the weight. So I have minus W times D plus C sine theta, cosine theta 1. And I have that plus RA times D and plus RB times D plus C plus B, because the total distance of RB from C is D plus C plus B equals to 0. So this is my relation number 1. Okay. Now you could have selected any other point. You can do sum of moment about A, you can do sum of moment about B, or sum of moment about G. So you are free to select the point that is convenient for you. Okay, so this is my first relation. Now, the next one is to, I can do sum of forces now. The easiest way is to do sum of x equals 0 and sum of y equals 0. Of course, here, the best frame to select for x and y is along the incline and parallel to the incline, okay? Because in this frame, I have already RA and RB are along y. So I don't have to project them, to do any projections for RA and RB. Now, of course, for F2, I should decompose into two components, one along X, which is F cosine theta 2. And one along Y, which is F sine theta 2. Okay, and finally for my weight also, I should decompose my weight. My weight, you know that we used a lot the decomposition of weight on an incline. So because the angle with the incline here is theta 1, this is theta 1, then when you draw the weight is perpendicular to the horizontal. So it's doing an angle with the incline equal to 90 minus theta 1. So when you project the weight along the incline, along X, it's a negative projection because we considered X upward. So the projection of W on X is negative, and we do minus W or cosine 90 minus theta 1 or sine theta 1. Okay, and for finally to get if you want the component along Y, it's a negative component along Y, and since the angle here is theta, so theta 1, so you do projection of W minus W cosine theta 1. Okay, so now if we write the equations, we have sum of x equals to 0 will give us plus f cosine theta 2 for RA and RB, no projection, minus the weight sine theta 1, so minus W sine theta 1 equals to 0. This is equation, this is the second equation because we already wrote the moment equation. Now, the third equation is sum of y equals to 0. So number 3 is sum of y equals to 0. So then you get from relation number 2, okay, you can get the value of f. So you can get f from here. And now for relation 3, you will relate. You will find another relation between RA and RB. Already you found the first relation between RA and RB by doing sum of moments about C. So now when you want to find what is RA plus RB, then you have that plus RA, because it's along Y upward, plus RA plus RB. Don't forget the projection of f, which is plus f sine theta 2. And you have also minus the projection of weight on y, which is W cosine theta 1. So minus W cosine theta 1 equals to 0. And this equation will give you an additional relation between RA and RB. If you solve, and F, you know it from equation 2. So now if you take equations 1 and 3, you will have two unknowns in these equations. You have two unknowns, which are RA and RB. So you can solve for these unknowns. Okay? Any question on this?
نعم سؤال
نعم.
هنا مثلا
Yeah.
نحط مثلا الارات نحطه ماينس والويت نحطه بلس.
ايه مظبوط فيك، بس ساعتها بتكون عم تاخد البوزيتيف دايركشن لتحت. You can of course. إذا عم تاخد البوزيتيف Y لتحت بيصير ال W ال projection of W positive وال projection of RA RB و F negative.
اوكي انا باخدها مثل ما بدي.
ايه اكيد. اوكي. مش مهم بس تاخدها to يعني to set، يعني بس تكتب الايكويشن to stick with your direction، مش انه بتاخدها شيء وبتعمل
خلص كله
projection
هيك.
شيء. اوكي.
يس.
Other questions on this? So let us continue. Okay. A picnic table has a weight of a total weight of WT and the center of gravity at GT. If a man weighting WM has a center of gravity at GM and sits down in the centered position shown, determine the vertical reaction at each of the two legs at B and neglect the thickness of the legs. What can you conclude from your results? You know that whenever we design a table, a garden table, let's say, we consider that we should have safety issues to not have overturning. And when you design your table, you should work on what should be the weight of the table. It should be high enough to not have whatever, we consider, let's say this table is for 4 persons, for example. So if it is for 4 persons, then we should design based on that. If we have even with a safety factor, of course. So if we have a very high, we consider the maximum possible weight. Let's say per person, we put maybe 150 kilograms to be on the safe side. And we take the most critical case. And if all persons will sit from one side, the table should not overturn. This is how we can determine what will be the weight of the table and what is the distances separating, if you want, reaction supports from the center of the table. So this problem will give us an idea on the relation between these variables, the distance between the leg A and the center, this is B, the distance between reaction and B and the center. So here you have 2 legs from each side, and 4 legs in reality. So here you have 2 times leg at A, 2 times reaction at A or NA. And here also because you have 2 legs, and always, as I told you, the reaction of contact, the normal, is perpendicular to contact. The contact line between the ground and the table is the horizontal line. So NA is up and NB is up. And because we have 2 legs, so you have 2 NA and 2 NB. Now, what is the idea of design here? Let's say we have an occupant from this side. So of course, the presence of the occupant will tend to create a moment about the center of the table, okay? Or about B if you want. We'll try to cause a certain moment and do an overturn of the table. And imagine that the weight here is very, very large. What will happen is that you will do overturning of your table, and then it will lose contact with B. يعني تخيلوا إذا كتير عالي الويت هون شو بيصير؟ I just lose contact with B وبتبرم التable around A. Okay, this should be avoided, of course. Okay, I should do the design in a way to not have any possibility of turnover. Now, how can I know if there is a possibility of turnover or not? I will solve for the normal reaction at B. And I will say that to be on the safe side, this normal reaction should be positive, larger or equal to 0. يعني على most critical condition بتكون equal to 0. يعني إذا بعد بزيد the weight of the man, I will have overturning of the table. Okay. Now, if I do to get NB, if I want to find what is the expression of NB, the best equation to write is what do you think? What is the best equation to write to get the value of NB? If you look at your figure, okay, شو هن الأنون تبعنا؟ عنا عنا NA, عنا NB, and we want to find one of these reactions. We want to find NB. حتى we will try to design, if you want, the weight of the table. Find a condition for the weight of the table to be on the safe side. Okay, so now if we look at our figure, in order to get NB function of W table, we should find an equation which will not consider NA. يكون عندنا equation without NA, we can do sum of moments about A and set it equal to 0. This will allow us to find NB function of our other variables. So let me write sum of moments about point A equals to 0 to find a relation between the normal reaction and the weight of the table. So if you look at the figure, you have the normal at A, but it will not do any moments about A. You have, we said we have 2 legs, so 2NA. We have also 2NB. Now, what is the weight of 2NB? What is the moment of 2NB about A? This force tends to produce a counterclockwise moment about A. And what is the distance between the two? The distance between the two is the distance from A to B, which is B plus C. So this term here, 2NB times B plus C, will represent the moment of NB about A. Now, what about the other forces? We still have the weight of the man and the weight of the table. The weight of the table here also tends here to rotate about A in opposite direction, which is the clockwise direction. So it's tending to do a negative moment about A. And what is the distance between the weight and point A? If you look at your figure, if you do the perpendicular, this is the weight direction. If you do the perpendicular from A, the line of action of the weight, it's equal to B. So it's a negative moment equal to minus W table times B equals to 0. Now, we still have just to find the expression of what is the moment of the weight of the man. The weight of the man is from the other side. So it tends to rotate about A in the counterclockwise direction. And to get the distance, this is the line of action of the weight of the man. Its distance from A is equal to this length here, which is A. And because it's trying to rotate into the counterclockwise direction, which is my positive convention, so my total equation will be 2NB times B plus C plus weight of man times A minus weight of table times B equals to 0. Now, how can I benefit from this relation? I can get NB function of WT and W man. And you can see that because the condition of NB, it should be larger than 0 to be on the safe side, to not have overturning of the table. Then you can find what should be the minimum value of the weight of the table to not have overturn. So the weight of the table should be larger than omega of the man